So let's see, last time we were talking about, we noticed that there was actually pi character in this trigonal planar molecule. So then the question becomes, how does that affect how we look at the resonance structures? Okay. So if I take BF3, that's definitely one of my structures. Okay. And so I know that then the resonance is going to start doing this. Okay. And it can go, and that can go all the way around. Now, before we had looked at these molecular orbitals, this might have been all you would predict. Because again, if you're just coming off gen chem knowledge, you're like, well, I mean, you got those single bonds, but now there's nothing else. Well, you start, so you say, but you saw those empty, those p orbitals sticking up there. So you had lone pairs, and we talked about that, right? So you had lone pairs on the fluorines and then empty p orbitals on the boron that can start to interact with each other. So now you know that your resonance is going to have to take on a few more structures. And so we have three brand new resonance structures there that previously we wouldn't have been able to predict without the actual molecular orbitals. Now, again, these resonance structures are schemes trying to explain what's actually occurring. The whole point is, well, it's like I told you in year one. This stuff can predict some things, but when you start actually getting like the solid wave functions and you see these molecular orbitals, you start to realize that the hybridization, the resonance, all that stuff is really just trying to explain the fact that these come together and form unique wave functions. And so the orbitals of the atoms will come together and form and combine to form a unique wave function in a way that allows the electrons to hold the molecule together and space apart. And so you essentially go from a bunch of orbitals to single structures that is filled with potential differences.
Right. So you're saying like, if I'm thinking about this molecule, it's going to be in reality more like a mixture of everything.
Yes.
Yeah.
So basically it's like, yes, the electrons are more like a fluid than they are anything else.
Yeah.
The molecule comes together, certain energy structures have to be filled.
Yeah. So it's not like moments in time where it's like this. Like
Right.
we can induce this, but it's not.
Yeah. So yeah, if we brought a polar molecule close, we could move the electrons around and get a different structure. But the electrons are going to come in, and the orbitals you knew are going to cease to exist, and they're going to form these brand new structures. And that's why we have to start thinking of them in terms of symmetry as far as their energy levels and their reactivities. Because I mean, these electronic structures, as I said, they're going to be unique to the molecules, and so you're essentially having to resolve the wave functions every time you make a molecule. And again, that comes from what they call the linear combination of atomic orbitals method.
I remember talking about that in bank then.
So it's just, it's because some people in Gen Chem are always like, well, why can't you tell us the whole story? Well, there's more to it. It gets kind of abstract. I mean, because we have all these schemes to explain what's going on, but the electrons themselves, they say, okay, now we formed a molecule. What are the discrete quantum states available? Okay, now like a fluid, we have to fill those. And you can still see the character of some of the atomic orbitals, but so, okay, let's think about the resonance structures of the NO double bond. Let's see. So why do the resonance structures for nitrate? Why do they not include two NO double bonds?
So this is like a T-shaped one, right?
Nope.
No?
Nope.
Oops. T.
Let's kind of review what happens with nitrate. Okay, so let's go back to just like some Gen Chem, where I remember that my nitrogen has 5 valence, my oxygen has 6. The first thing I'm going to do is I'm just going to make single bonds. And then, of course, everywhere there's a single electron, I'm putting a bond. And so I've used all 3 of those for the nitrogen, and I've used 1 of those for each oxygen. So now I'm just going to replace what I didn't use. So there. Oh, need more room here. And then on each oxygen, we get this. Okay, now start asking ourselves, where do electrons go?
This was the thing where like one of the oxygens gives its
Right.
electron.
Yeah, so like, let's say we go there, one of those goes there.
And then we pull another one out.
Right now, so this is also, we want to make sure we're obeying the octet rule. Because we don't want, nitrogen's way too small to start going hypervalent. Now, oxygen we know is more electronegative than nitrogen. So what it's going to do is it is going to pull an electron to itself. But see, we still have space open up on the oxygen on top. This is where the negative charge on the nitrate comes from, because we have an external electron that comes in to fill that hole. Okay, and so what we get, our first structure, well, we can do it this way. This oxygen itself, that oxygen is negative itself. So I'm not going to redraw in all of the lone pairs, but this is going to be our first structure. So remember that nitrate and just so you know, I didn't have to make that negative sign necessarily go counterclockwise like that. It seems symmetric to me. But so we remember that our 3 resonance structures are this. Okay, now, why is this all that's shown? Why don't we start seeing that more of that? So we're definitely going to see pi bonds and the double bonds, but the question is, let's see, why are there not multiple double bonds in this molecule?
Probably octet rule.
So that's one of them.
And then do we need to do the orbital thing?
Yeah, so you remember we saw multiple pi structures for the BF3. Do you remember why that was?
Because of the empty p orbital.
Right, so let's look at the p orbitals here. Okay, so let's just draw So what I'm going to do is I'm going to go back to trying to think. So what I'm going to do is I'm going to go to a structure that already has this electron that's come in and this electron that's gone here. Okay. So we're kind of looking at this sitting on its side. Okay, so we're going to get a p orbital there, p orbital there. So we're going to get orbitals like this. Now, what we have is this kind of structure here, where you can say that the negative can be on any one of these, either one of those. Okay. So what you notice is going to happen is that electron's going to go there and that one's going to go there to form a double bond. Okay. Now we know that those lone pairs on the other oxygens can shift around and that double bond can shift around. But what's happening here that's preventing more double bonds from occurring?
Those full orbitals.
So in particular, look at the nitrogen. Do you see that single electron on the nitrogen that's going to form the double bond? So now that p orbital has been used. There's no empty space there for these to just flow in and out of. That p orbital gets used for a specific pi bond, and now there's nothing left for those other lone pairs to reach over and enter into.
Okay.
So they actually can't do it. So yeah, the octet rule is maintained, but there's no space for those lone pairs to start forming more pi character.
This might be slightly off topic, but I'm just trying to like think about how orbitals look. And like, okay, if I have a triple bond going on, that's gonna be one of those orbitals where it's kind of like it's got the little tiny one, and then there's like two of them that are like that.
Oh,
that
a triple bond. Okay, how to think about this. So
sorry, I know that's off
no,
topic.
it's the triple bond is like the full cage structure. So like let's say we had let's just do this is a common triple bond that we know about. Okay. So what happens is first your carbons are going to form a sigma bond right in the middle. Okay. But we know that there's two p orbitals left over. Okay. So when those reach across and form the two pi bonds, let's see here. Okay, so we're going to get this sigma structure in the middle. Then, the three-dimensional drawing. Let's see if we can do this.
And that drawing, the blue and the green are crossing, right?
So one is up and down, the blue is in and out.
Okay, so the like shaded in blue is coming towards us?
Yes.
Okay.
Okay, so there's that one. Let's get the upwards. Okay, now Your triple bond is going to kind of have this kind of structure.
They're like perpendicular?
Yeah.
Okay.
So you get the up and down pi bond, the in and out pi bond.
Okay, cool.
Not the best artist, but it's not horrible. If you want good art, go to Khan Academy.
True.
They are really good at drawing stuff.
That's like a requirement to be a part of their team.
I think so. Okay. So let's see here. Now, I want you to work on this for a few seconds. This is pretty much what we just did with nitrate. I want to see if you can answer all the parts of it.
Yeah, that's actually. Okay.
Your head wrap makes me think we think the same, that there's 2 times in the year. There's Halloween, then like 1 month, then like December.
Yeah, that's true, actually. I agree. I think Halloween should be celebrated for way longer than Christmas is. Personally.
I still want to get a Christmas tree that's black, and I want bulbs that are jack-o'-lanterns.
That would be great. That would be awesome. Was it the Nightmare Before Christmas or whatever?
Oh, I love that movie.
That's a great movie. If all of it are actually friends.
I start watching that movie in October, and I just watch it all the way through.
Mm-hmm.
You need to watch 3 movies in a row. You need to watch Frankenweenie, and then Corpse Bride, and then Nightmare Before Christmas. Kind of a fan theory, but they're all the same person.
I've seen that before.
So
I agree.
The little boy in Frankenweenie becomes the groom, and Corpse Bride becomes Jack Skellington.
Yeah. Yeah, he gets reunited with his dog even. Like, it's perfect. Okay.
I know we're spending a lot of time on bonding, but a lot of the stuff that's in the textbook you can read.
Mhm.
If you start to understand how bonding works at a deeper level, your understanding reactivity is going to open up wide for you.
Yeah. I mean, bonding is like important for every single class I'll probably ever take. Like, it's so important.
And just kind of having a deeper understanding of the mechanism of it.
Mm-hmm. Okay, I think I'm good with this. I think I'm done with my guess at least.
All right, let's take a look at part A. Just draw the structure. Okay, well, I did this the old-fashioned way. I said carbon has 4 valence, oxygen has 6. Alrighty, so then I'm going to say, well, let me put a single bond on all of these. Replace the electrons I didn't use. I know at some point there's going to be another chemist who sees these videos and he's going to go, no, count up all the valence and put. I'm like, it's kind of what I'm doing, but that's a lot of work I don't want to do. So it's just
It's okay.
Okay, so-
achieve it.
now we know carbon is very, very strict about that 4-bond policy. Okay. So let's just do this. We notice that it's a 2 minus, so that helps us. So we have an electron come in there, electron come in there, and that's going to give us our first structure. Okay. So there's our first carbonate. Now, let's draw the resonance structures. This is B. There's our resonance structures. Now let's think about a bonding scheme. So first we notice that carbon is in a trigonal planar field. So we're gonna describe it as sp2 hybridized. Okay. Oxygen's a little tougher. Okay, so let's try to think about what kind of hybridization we would put on oxygen. Because the way it looks, it kind of looks like some of them are sp3 and one of them is sp2. But we know that it's not going to be that exact. The electrons don't really behave that way because if you've probably done this in organic chemistry, the actual structure we could draw.
With the dashed lines. Yeah. And then the partial negatives or whatever.
Mhm. Oh, so let's see. So it's 2 negative. Yeah. So I don't know what you could say, like negative 2/3 for all these. Okay, so it's more like this. But so if we see this, we know that there's not actually like hard set lone pairs on those oxygens. So what do you think that would reduce those to? Like all the oxygens are going to have what? A hybridization.
I guess they'd be SP3,
2.
SP2.
Yep.
Okay.
So you're going to want to go with the hybridization that you would see on the doubly bonded oxygen. Okay, so that means that our first type of bond are going to be sigma bonds between carbon and oxygen sp2 orbitals. Which actually helps because since they're all sp2 orbitals, they all have the same symmetry. Okay, so now our pi structure. So again, let's kind of look at it from the side. Okay, so once again, let's go back up to just our structure here where the 2 electrons have come in. Okay, so that's going to give us okay. So then our pi structure is going to be formed from the two p orbitals of the oxygen, an oxygen and a carbon, then that's going to resonate around.
So if we did the little program that makes the orbitals, it would have like two big clouds on either
Yes.
side. Okay.
Mhm.
Cool.
Okay, but what happens? So now,
No.
just one step up, XH2 molecules. Okay, so molecules that have multiple ligands. Okay, we kind of been doing that with those resonance structures. But how do we start figuring out the molecular orbital diagrams for more complex molecules? So again, like your XH2, CO2 would be a good example. On one of these, I used beryllium H2, so you could kind of see what it looked like. But so this is called the ligand group orbital approach. So now, instead of just looking at the orbitals on a single ligand attached to another atom, you're going to take a ligand group as a whole and look at its symmetry. So in this case, you have your central atom. You're going to look at its symmetries and its orbitals. Then you're going to take like for example, the H2, the two hydrogens off as a single group. Now, this is easier to look at because you notice that each one, that the hydrogens only have a 1s. So we only have two possible symmetries. So ligand group 1 is where they're both in phase. Ligand group 2 is where they're out of phase. Okay. And so then we're going to start to get molecular orbital structures that are a little more complex than what we've dealt with before. So, one of the things we've done this time is we've oriented the z-axis that way, okay? So when we start looking at this, we have our two options for our hydrogen s orbitals. And so then we notice that we can get different interactions here. So on the bottom, we can get a 2s orbital from our central atom interacting with the 1s orbitals of hydrogen to form a perfectly symmetric bond. Okay, so now when we're looking at that, that one's actually going to have to go all the way down to the psi 1, okay? Because you have low energy orbitals forming a perfectly symmetric field that's going to go pretty low in energy. Now, you go up top. Now that may be a p, so that's going to be a 2pz orbital interacting with the s orbitals. But you can get a couple of combinations there. You can get an antibonding combination if you flip that pz around. You can get a bonding combination when you have the pz like this, where you have the phases lining up. And if you look at the symmetry of those, they have the exact same symmetry. So imagine like your z-axis is a C infinity axis. Then start looking at your other axes. Every single rotation or reflection I do at the LGO2 matches. It's going to match that pz orbital. So you can see how they have the exact same symmetry. So they're going to be able to make bonds. Now, in that one up there, you will get an actual antibonding interaction. Can you figure out how that becomes antibonding? Well, no, hang on, never mind. It will become antibonding. Just forget that part. This is going to form sigma bond to the right, sigma bond to the left. Okay, you'll see in a little bit how we get antibonding out of some of these. So I was going to say you get antibonding at the nodal center, but no, that's actually on the central atom. So it's not on the bond itself. So you're going to get sigma bond, sigma bond. Oh, and I want to talk here. You see these two in the middle?
Yeah.
Now you're going to start getting orbitals we call non-bonding. Because as you notice, if we put the 2px, 2py in there, they're not really providing a symmetry that we can use very well. So those are going to start to be, so you're going to see various combinations of non-bonding orbitals. Okay, so let's start taking these apart and thinking about what these are. So look, so here's your beryllium H2. This is your psi 1. So we said that this is going to be, so this perfectly symmetric representation is the lowest energy, and it's going to be a combination of what?
It'll be the S's.
So you're going to get a hydrogen S. So kind of like this. You're going to get those S's interacting with each other, and when they combine, you're going to get this completely symmetric electron structure. Versus the next one, what do you think interacts?
It's got to be S and the PZ.
Yep. So we're going to have an S on this side. An S on this side. So now this one over here is going to be the other phase. So this comes from our LGO2. So then we're going to get our PZ orbital that goes in the middle and lines up. Now, this one's going to be higher in energy. Why?
Because of the P.
Right. So instead of SSS, we have an SPS. So we're getting a little bit higher energy out of the character. Now here, I just went ahead and wrote out what's going on. Your Psi3, Psi4, you see your PX and your PY are just really not, because again, you'd have your S's.
They're not head on like they need to be.
Right. They're just kind of out there in space, and they're not really going to provide the proper sense. So you would get equal bonding. So let's say, so here you get like some bonding character from there, but you get equal anti-bonding character from there. So these are just not really going to contribute.
Right. Okay.
They're not in the proper orientation or symmetric in a way that could be active in the bonding.
Yeah.
So now you have these two non-bonding orbitals. These two non-bonding orbitals are going to be degenerate because either these are the two p orbitals. Now, if you look at where beryllium's out on the periodic table, you're going, why am I talking about two p orbitals? Well, because we're at the n equals 2 level. It's time to remember that these orbitals exist based off the quantum level, even if they don't have electrons in them. Here are some interesting ones. So let's go back to our diagram. Okay, so we have, what the heck just happened? Okay, so we have bonding, bonding, non-bonding, non-bonding. What do you think these up here are?
Antibonding?
Anti-bonding. So these are going to, well, I'm not going to put psi star on there. That means something completely different to quantum theorists. So we're not, let's just avoid that. We'll just call those anti-bonding. Okay, now let's look at these. What orbitals do you think are coming into play with these?
It's got to be the. I mean, I know it's S, and then the one that's like px squared plus y squared. Is that what it is? No, those are for D.
No, those are D's.
Oops.
It's still going to be your PZ orbital.
It's still PZ.
Which one is 3 S's? Which one is SPZS?
SPZ. Wait, say that again. Sorry.
One of them involves 3 S orbitals. The other one involves 2 S orbitals and a P orbital.
That's S and that's got.
Right. So if we look here.
So this is just because they're opposite phases. Okay.
Now, because what we could say is, I'm just going to go ahead and put a big S orbital in here. And I'm going to make this S orbital be an opposite phase. So you can see what happens is as it interacts with those S orbitals on the hydrogens, it gets sandwiched. And that's where you get that structure in the center. Versus psi 6, Let me get my LGO2. And my PZ orbital. So again, as they interact, those p orbitals get sandwiched a bit and they flatten out kind of like that. Now, which one of these would be the lower energy one?
The one on the left? Question mark?
The what?
The one on the left?
Why?
I mean just the S.
Yeah, because you're dealing with lower energy orbitals. All righty.
Okay. Again, maybe a question I should know the answer to, but the sigma 5 or hello, the psi 5
Yeah.
and the one that was like, was that psi 1 where
Yeah.
so
there.
Yeah. Is it is the two different phases, are they both equally there at all times? Or is it like something happens to make me switch between my beryllium S orbital being in one phase versus the other?
So that's gonna kind of get back to a Schrodinger's cat kind of thing.
Okay.
So it depends on how the electrons come together, which electrons come together. You can get in phase or out of phase orbitals. For your multi-lobe orbitals, you're always going to have an equal number of in phase, out of phase. Your S ones, it's really going to depend on which electrons come together and how they do it.
Mm-hmm.
And so then, yeah, so kind of at all times they both are there, and you're getting so then when they interact to bond, they're going to start to split. And so what was there together before in kind of a linear combination, so a superposition kind of situation, when another orbital comes in to form a bond, they're forced to start splitting. This is a kind of a good thing to keep in mind because a similar thing's going to happen when we start talking about crystal fields. Mm. So now I have so your S orbital there of a different phase comes in. And so as those two possibilities start to split, one goes lower in energy, which will form your psi 1. The other one goes higher in energy, which will form your psi 2.
I see. And that'll the lower energy one will fill up faster.
Right? Yeah, because then the electrons are going to fill according to the off-ball principle.
Yeah. Okay.
So as we go through, actually, your questions mean that you're starting to understand quantum mechanics because remember, any person who comes to you and says, "Oh, I understand quantum mechanics," they've never studied quantum mechanics. Because the more you study it, the more you look at it and go, "What?
What's going on?"
So, because here's the thing, like when you get really deep into electronic structure, you start working with. I mean, it is a mathematical construct, but it's also kind of a definition of a space. You start working with things like Hilbert spaces and whatnot. You have to use them to solve for electrons, but you realize that these electronic systems exist in a hyperdimensionality that we cannot comprehend. Mm. So to us, it looks like two things are happening at the same time. No idea what that looks like in a higher dimension.
Mm. Okay.
Because I mean, you look at a piece of paper as something simple, like a 2D surface. It's because you're three-dimensional. Mm. You know, imagine something that can access 4 dimensions, 5 dimensions, so on and so forth. Mm. You know, it looks at us like we're just a straight line. You know, and I say looks at us, and some people might go, "Dude, don't anthropomorphize the electrons." I'm like, yeah, no, wait a minute.
I want them to be anthropomorphed.
Yeah, because they do actually know if they're being observed. I don't know how.
That's sick.
But there was an experiment performed. It was the double slit experiment over again. But the person put a detector on to know when a particle went through. When the detector was off, they got the wave pattern. When they turned the detector on, the wave pattern went away and collapsed into a single bright spot, or a particle pattern.
That's cool.
The electrons knew when the detector was on. Huh. They were able to tell that they were being watched. So, yeah, makes you kind of go, I don't get it. Okay.
I don't know what's going on.
So we're gonna have to expand our our ligand group orbital method to include point groups now. So we're going to start bringing in character tables. Okay, now the first one we looked at, that was a D infinity H. Yeah, we're not going to start with that character table. But we're not even going to get into D infinity H in this class. That is like a doctoral level kind of character table.
Okay.
Give it a look sometime. You don't want to take that one apart. But we're going to start with an XH2 that's a little more simple. So our bent water. Okay. So let's see. So what we're going to do is use the character tables to assign symmetries. I hope you've realized by now that the series of ones and minus ones is either symmetric or anti-symmetric under a certain operation,
Sure.
symmetry operation.
Yeah.
You remember that we're limited to the symmetry groups in the table. So like here, the orbitals can only be A1, A2, B1, B2. We can't have A1 prime or A2 double prime. We can't have B2 prime G. We're limited to this table. So what we did above was just kind of constructing these orbitals by observation. What we're going to start into on Monday is we're going to start constructing these by actual symmetry operations and comparing them to the character table. The character table. Let's see. So this is going to be something that you'll notice. We can only use orbitals that can be classified within the symmetries of the table. All other orbitals are out. And then we're also only going to be able to combine orbitals with the same symmetry. Okay, so this is why I started talking early on about orbital symmetry, and it becomes super duper important. Because now orbitals are not going to combine. Like you're not going to combine a B2 and an A1. It's just not going to happen. You're going to have combinations of A1, A1, A2, A2, so on and so forth. Okay, so we will start taking apart water on Monday, just kind of go from there.
Cool. Sounds good.